Hi everyone, welcome back to Chem Story. Today, we're going to talk about how ethers and epoxides react, specifically how their carbon-oxygen bonds can be broken. We'll focus on two key reactions, ether cleavage and epoxide ring opening. Now, ethers are usually pretty stable, but under the right conditions, especially when you use strong acid, those CO bonds can be broken in a controlled way. So in this lesson, we'll break it down step by step and take a closer look at how these reactions actually work. Let's start by thinking about how reactive ethers are in general. The short answer? Not very. That's because ethers don't have a good leaving group. And without one, they're usually unreactive under normal conditions. They don't go through SN1 or beta elimination the way alkyl halides or alcohols do. And if you try to hit them with a strong nucleophile, it doesn't work because the leaving group would be an alkoxide, which is a strong base and a poor leaving group. So if we want to break an ether, we need to activate it first. And the way to do that is with a strong acid. Only under acidic conditions can the ether oxygen be protonated, and once that happens, everything changes. The oxygen becomes reactive, and cleaving the CO bond finally becomes possible. So what happens when we treat an ether with a strong acid, like HBr or HI? Now things start to get interesting. The acid protonates the ether oxygen, which makes it much more reactive. Once that happens, depending on what kind of groups are attached, one or even both CO bonds can break. If one side can form a stable carbocation ion, the reaction tends to follow the SN1 pathway. But if it's a methyl or primary group, it usually goes through SN2 instead. In the end, you'll get alkyl halides and alcohols. Or if both sides react, you can get two alkyl halides plus water. So when you treat ROR' with excess HX, you end up with RX, R'X, and a molecule of water. Now let's look at a couple of examples to see how this actually plays out. In the first case, we've got a cyclic ether with an ethyl group. When it reacts with excess HBr, both CO bonds break. The ring opens up. The ring carbon gets a bromine, and the ethyl group becomes ethyl bromide. And, of course, water is formed as a byproduct. In the second example, we're reacting methyl tert-butyl ether with HI. It's the same idea. We're using two equivalents of acid here, too. The tert-butyl group turns into tert-butyl iodide, and the methyl group becomes methyl iodide plus water. These are great examples of how strong acid can break even stable-looking ethers, as long as the conditions are right. Now let's talk about how ether cleavage actually happens and which mechanism it follows. It all comes down to the R group attached to the oxygen. If it's tertiary, benzylic, or allylic, the reaction usually goes through SN1, since those carbocation ions are relatively stable. But if the group is primary or methyl, then SN2 is more likely, because those carbocation ions would be too unstable to form. So just by looking at the two groups on either side of the ether, we can often predict whether it'll follow SN1 or SN2. Let's break it down with an example. Tert-butyl methyl ether, and walk through how it reacts under acidic conditions. First, the ether oxygen gets protonated by the acid, which makes it a much better leaving group. Then, the bond between the oxygen and the tert-butyl group breaks, forming a tertiary carbocation ion, which is nice and stable. Once that carbocation ion forms, the bromide ion comes in and attacks, giving us tert-butyl bromide. At the same time, the methyl group leaves as methanol. Now remember, in the first step we formed tert-butyl bromide and methanol, but since we're using excess HBr, the methanol doesn't just sit around. It reacts again, and this time, the reaction follows an SN2 mechanism. Here's how it works. First, the oxygen in methanol gets protonated by HBr, turning it into a much better leaving group. Now that the oxygen is positively charged, it's ready to leave. Then the bromide ion comes in and does a backside attack on the methyl carbon, classic SN2. That breaks the CO bond, giving us methyl bromide and water as a byproduct. All right, let's shift gears and talk about epoxides. They're still a type of ether, but because they have a three-membered ring, there's a lot of ring strain built in. And that strain makes them much more reactive than regular ethers. Even though epoxides are small, they're very eager to open up. The ring breaks through a backside attack, just like in an SN2 reaction, That means the nucleophile attacks from the opposite side, which inverts the stereochemistry at that carbon. And since the bond angles in a three-membered ring are only about 60 degrees, breaking the ring relieves that strain, and that's what drives the reaction forward. Let's take a look at what happens when epoxides react under different conditions. In basic conditions, with a strong nucleophile like methoxide, the ring opens up and gives a product with a methoxy group and a hydroxyl group on neighboring carbons, and they end up trans to each other. But under acidic conditions, like with methanol and sulfuric acid, the ring still opens, but this time, the methoxy and hydroxyl groups show up in different spots, so the regioselectivity ends up changing. So depending on whether the reaction is acidic or basic, you'll see the same types of groups in the product, but their position and orientation can be completely different. Let's start with basic conditions, or what we call nucleophilic conditions. This one's a bit more straightforward. A strong nucleophile directly attacks one of the carbons in the three-membered ring. But it doesn't just hit any carbon, it goes for the less substituted one, because that spot has less steric hindrance and is easier to reach. And since this follows an SN2 mechanism, it all happens in one step, with a backside attack that causes inversion of configuration at that carbon. Let's look at an example. We've got a dimethyl substituted epoxide, and methoxide is acting as the nucleophile. It attacks the less substituted carbon from the backside, which opens up the ring. Then the oxygen picks up a proton from water to finish the reaction. The final product is an alcohol, with an OH group and an OCH3 group on neighboring carbons. And the stereochemistry? It's exactly what you'd expect from an SN2 backside attack, clean and inverted. Under acidic conditions, the reaction shifts a bit. The epoxide gets protonated first, which activates the ring and makes it more electrophilic. Then, instead of going for the less substituted carbon like in basic conditions, the nucleophile attacks the more substituted one. The mechanism here is often called a loose SN2. It's still a one-step reaction, but there's some partial carbocation ion character that develops along the way. In this example, the epoxide is first protonated by sulfuric acid. Then, methanol attacks the more substituted carbon. After losing a proton, we end up with a trans product, with one OH group and one OCH group on neighboring carbons. And here's the key part. The regiochemistry is completely reversed compared to the basic case. So here's the bottom line. Under basic conditions, the nucleophile attacks the less substituted carbon. Under acidic conditions, it goes for the more substituted one. The mechanism shifts from a typical SN2 to what we call a loose SN2, where the transition state has a bit of carbocation ion character. And that difference in mechanism is exactly what leads to such different regioselectivity. Alright, that wraps up our lesson on ether cleavage and epoxide ring opening. These reactions might look simple, but once you understand how the mechanism shifts depending on the conditions, they become really powerful tools in synthesis. Thanks for watching Chem Story, and as always, I'll see you in the next video.